Hey guys, welcome back to this channel, and today we'll be continuing our series about aerobic respiration. So I have previous two videos on the previous two steps, and this one is going to be about the Krebs cycle. So this is pretty exciting because I think the Krebs cycle is really associated with aerobic respiration, so it's finally fun to get to know it. So just as a quick recap, our step one was glycolysis. And again, if you're not familiar with these steps, I highly recommend you go watch my videos because you won't really understand what's going on here and where all these reactants came from. But nevertheless, of course, you can try. And so step one was glycolysis, where we turned glucose into 2 times pyruvate. And then step two was the link reaction, where we turned our pyruvate into acetyl coenzyme A, or acetyl-CoA. And glycolysis occurred in the cytoplasm, but the link reaction, like the name might suggest, connected the cytoplasm to the mitochondria, or the matrix of the mitochondria. And now we're finally on to the Krebs cycle. So the purpose of the Krebs cycle is to produce a lot of reduced NAD and then reduced FAD. You'll see what I'm talking about later. And again, just as a quick recap, NAD is our electron carrier, so once we oxidize something, it gets reduced and it carries these electrons to the final step, which is the electron transport chain, but we're not going to get into it here. All you have to understand is that reduced NAD is necessary for aerobic respiration, hence us producing so much of it. And the location of the Krebs cycle is in the matrix, so in the cytoplasm of the mitochondria, basically. Again, because we just had the link reaction, which connected the cytoplasm to the matrix, and now we're in the matrix. So let's get into the fun stuff. So if you remember, or just like I said right now, after the link reaction, we ended up with an acetyl coenzyme A. So it had 2 carbons, which I will represent with circles, and a coenzyme A. Now, the first step to the Krebs cycle is that the coenzyme A leaves it. And the reason we have the coenzyme A in the first place is because it helps the acetyl travel towards the Krebs cycle or enter it. And now that it's here, we don't need it anymore. And now we're left with just acetyl. Now, if you know anything about a cycle, you know that it goes from start to finish, which is the start again, right? So now, before, in this previous cycle, our product was oxaloacetate. And the name might sound a bit scary, but all it is for us is a 4-carbon molecule. Now, acetyl and oxaloacetate will react together and produce citrate. Again, kind of a complicated name, but it's really just a 6-carbon molecule because we have 2 carbons plus 4 carbons. Now, if you think about cellular respiration, what are our byproducts? Well, our byproducts are carbon dioxide and water. However, if we look to the past or to our past steps in our previous videos, we haven't produced any of those yet, right? So now we have a lot of carbons, right? And we have to end up back with a 4-carbon molecule. So we're going to get rid of these 2 carbons and produce carbon dioxide as a byproduct. And again, the loss of a carbon is called decarboxylation. And so we're going to have decarboxylation of citrate. And we're also going to oxidize it. That means it's going to lose electrons, and NAD is going to gain electrons. Again, oil rig. Oxidation is loss of electrons, reduction is gain of electrons. And so now you can see we've ended up with a 5-carbon molecule. I'm just going to leave it as a 5-carbon molecule, not give it a name. And we have produced carbon dioxide, and we have reduced NAD as a result of oxidizing citrate. Now, we're still not at our 4-carbon molecule, so this is going to be one more time, and we're going to lose another carbon, and we're going to oxidize this 5-carbon molecule. As a result, we will have a 4-carbon molecule. Now, we have a 5-carbon molecule, but it's still not oxaloacetate, right? Because the carbons are correct, but what about the hydrogens or any other atoms that are here? So now we're going to do our last step, which is actually a pretty big step, but it involves a lot of components. But this step will actually get us from this 4-carbon molecule back to oxaloacetate, completing our Krebs cycle. So in order to get from this 4-carbon molecule to oxaloacetate, first, we are going to have to oxidize it again, right? But we have to do quite more oxidations, so NAD is not sufficient enough. So we're going to introduce a new electron carrier, which is going to be FAD. And I'm just going to highlight it because we haven't come across it yet, so just making sure you won't forget it. And now, as you can see, there's quite a lot of redox reactions going on, redox being reduction and oxidation. And this actually will give us enough energy to join one ATP molecule with a phosphate and produce one ATP molecule. So as you can see, quite a bit is happening in this step, and there's 3 components: the NAD being reduced, the FAD being reduced, and the ATP production. But this is it. We have completed our Krebs cycle, and I'm just going to highlight all the terminology that is new. And it's actually, if you think about it, only these 2 molecules, citrate and an oxaloacetate, and the FAD, the electron carrier. Now, let's just summarize this. So, how many oxidations have there been? Well, we have an oxidation of citrate right here, in this step right here. Anytime we produce a reduced NAD, we have an oxidation, basically. We have an oxidation right here, one right here, and FAD is also an electron carrier, so it also oxidizes the 4-carbon molecule while getting reduced itself. So if we count that together, we have 1, 2, 3, 4. 3 of which are driven by NAD, 1 is by FAD. However, this is for 1 acetyl, which comes from 1 pyruvate, which comes from half of a glucose. So per glucose, we're going to actually have not 4, but 8 oxidations. And the number of decarboxylations is 1, 2. Again, this is per an acetyl. So for glucose, it's going to be 4. And how much ATP have we produced? Well, per acetyl, we have produced 1 ATP. So per glucose, we're going to have produced 2. And the reduced NADs, like we've said, we have 3 of them, which then travel further on and help us create a vast amount of energy because, again, 1 ATP molecule is not a lot. We're still just building up all of our reduced NADs and FADs so that they can really produce a lot of energy in the last step in the electron transport chain. And we have produced 1 reduced FAD molecule, so 2 per glucose. So I hope this Krebs cycle made sense. If you have questions, ask below. And just remember that it's really only consistent of 5 steps, the most complex one being this last one. However, it's really not that complex because all you're doing is you're having oxidation and you're producing ATP as a result. So I hope you enjoyed. I hope you learned something new, and see you next week.